In this video, we're going to take a brief detour down the road of Jensen's inequality. So Jensen's inequality says that if you have a random variable x and a convex function phi, then the expected value applied phi of the expected value is less than or equal to the expected value of phi of x. Okay, so before we explain why this is true, let's just remember the definition of what a convex function is. So convex function is also known as a concave up function, as we see in calculus. So definition, function phi of x is convex if for x1 and x2 we have, actually, let me draw a picture first. Okay, so if I have x values x1 and x2, then the idea is that you're convex if the straight line that connects them lies above the value of the function. So what's the, how do I describe the x value of this point? Well, I'm starting at x1 and I'm going some, I don't know, let's call it p times the difference of the two values, x2 minus x1, where p is somewhere between 0 and 1. So I'm looking at some amount of the difference between them, so a fraction p between them. So this value right here is phi of x1 plus p x2 minus x1. And this value up here is, well, it's the straight line value between the two phi values. So it's you take phi of x1. You know, if I had my y-axis here is phi of x1 and this is phi of x2. And so I'm looking at the value that's kind of linearly between, it's the value that would be between these two values if I had a straight line connecting them. So it's a fraction of p amount of this distance between them. Okay, so it's phi1 of x plus p times phi2 of x minus phi1 of x. Okay. So you're convex if this value is always bigger than this value. But maybe I'll say it in a slightly nicer way, like, excuse me, if I were to kind of rewrite this, let me see if I can do it without messing up, but let's see. So, so what I'm really saying is that if I'm looking at 1 minus px1 plus px2, that's this thing here. And this thing is similarly 1 minus px1 plus sorry, not x1, phi of x1. I could have just told you the definition, but I'm kind of deriving it because I think it'll be more fun. Okay, so and then if I make the kind of the reasonable kind of change of variables, p1 is 1 minus p2 is p, then what this really looks like, let me give myself a little brim, so is the definition of convexity is that for 0 less than or equal to p1 and p2 less than or equal to 1, p1 plus p2 equals 1. If you have a couple of numbers like this saying kind of how you're averaging in some sense between these two values, then if I look at p1, sorry, phi of p1x1 plus p2x2, that thing right there, then that's less than or equal to p1 phi of x1 plus p2 phi of x2, which is that thing right there. That thing right there. Okay, and this is the definition of convexity. Okay. That's the definition of convexity. Let's actually give a slightly more general equivalent notion. So in fact, maybe this will be a proposition. Let's say phi of x is convex if and only if we're given x1 through xn, some x values, and some p values, p1 through pn, between 0 and 1 with the sum of the pi equals 1, then if I look at the at phi of the sum of the pi xi, that's less than or equal to the sum of the pi phi of xi. So in the case where I equals 2, this is the original definition of convexity, but this is with endpoints. So let's just prove this. So of course, this is obvious because this is the case n equals 2, but for the converse, so we'll prove it by induction. Induction on n. So n equals 1 is vacuous. It's just an equality, I guess. Well, n equals 1. Does that make sense? Let's just focus on n being at least 2. So for n equals 2, it's the definition. What does it look like for n equals 1? Sorry. Right. For n equals 1, it's just that phi of x1 is x1. For n equals 2, it's the definition. Okay. And for the induction step, what do? So we're assuming that it's true for n minus 1, and I'll prove it for n. So I'm going to write the sum xi, I equals 1 to n, as the sum, let's say, p1 x1 plus the sum I equals 2 to n of pi xi. And now let me p1 x1 plus, now let me multiply and divide by 1 minus p1. Okay. Now, the nice thing about doing that is you notice that if I take the sum from I equals 2 to n of the pi, what do I get? I actually get 1 minus p1, because the sum of all the pi's is 1, right? So that is to say that that if I looked at the sum of the pi's over 1 minus p1, I equals 2 to n, then this is actually equal to 1. Okay. In any case, but that's not the first thing that's important. But that'll come up in a moment. This is by the definition of convexity, less than or equal to phi of less than or equal to p1 phi of x1 plus 1 minus p1 phi of this sum. Minus p1 xi. Okay. Just because p1 and 1 minus p1 add up to 1, so that's just the definition of convexity. And, this is then by induction, so this is by definition of convex, and then by induction, I can kind of pull apart that second expression. So this phi of that sum, these are a bunch of coefficients that add up to 1, but there's n minus 1 of them instead of n of them. So this is less than or equal to taking the weighted sum, I equals 2 to n, pi over 1 minus p1 of the phi of the xi's. Okay, and now I can just distribute 1 minus p1 sum I equals 2 to n pi 1 minus p1. What am I doing? I didn't actually do anything. I should have distributed, excuse me. We distribute that in, and we just get the sum I equals 2 to n of pi phi of xi, and that's, okay, we're done. We're done, right? This is the sum of the pi phi of xi. Okay, now actually we've now just proved Jensen's inequality in one specific case, actually. We've proved it, let's see, in the case of a discrete probability distribution. So note, this says that this exactly says that if I have some random variable, if let's say x is given by the probability function p of x, some discrete random variable, say finite, then the expected value of x, applying phi to that, what is that? That's the sum of the xi's pi's. And this is less than or equal to the sum of the pi's phi of xi's, if phi is convex. And that is, by definition, the expected value of the random variable phi of x. Okay, so we've actually just proved Jensen's inequality in the case of a finite random variable. For now, we'll skip the continuous case of Jensen's inequality, but one can do it extrapolating from the finite case by use, for example, of Riemann sums if you have a continuous function, continuous probability density function.